Uh, Welcome everyone to the One World Combinatorics on Words seminar. Um, our speaker today is Gwenaël Richomme from the University of Montpellier, and he's going to speak to us about some two binomial coefficients of binary words, geometrical interpretation, partitions of integers, and fair words. So Gwenaël, please.
Okay, hi everybody. Thanks for the introduction. So, well, it doesn't work. Okay, so let me start the talk with giving you some ideas of the origin of the work I was going to present you. In 2009, Anton Cherny introduced the notion of fair word. A fair word is a word such as for whole couple of letters A and B, the number of occurrences of AB as the third word in W is exactly the same as the number of occurrences of the third word BA. And Charlie makes some studies on this word, and one question that interested him, what could we say about the number of words? He made a conjecture, but this conjecture was not exactly true. As we can see in a paper written a bit before, written by Helmut Prodinger in 1979, which also studies these words under another name, and he answers give some answers to the binary case of the question of what can we say about the number of fair words. The terminology was, of course, different. Fair words was seen by Helmut Prodinger as a generalization of unrestricted Dick words. We'll explain that later. And when I look, when we know that Dick words can be represented as some particular words on the planes, so came to me the question, well, can fair words and maybe the binomial coefficient WAB, which represents the number of occurrences of AB in W, maybe these notions can be also geometrically interpreted. And the aim of the talk is to present you some observations around this question. I will provide you an easy interpretation of fair words and the binomial coefficients. I will show you also how this interpretation can be used to explain some known results on the two binomial equivalents. And with also this view of these notions, I will introduce you maybe some quite new structural information on the two binomial equivalent class of the word W, showing you a link with the lattice of partitions of the integer, which is the number of occurrences of AB as a subword of W. And finally, I will go to properties of fair word and show you a question what's given in the on the web that about this, not on this word, but which is related and related to another quiz approximation method, which is the least square approximation. Let me, before starting, say you that the results were already partially presented at a workshop at Liège in May 2025. And if you are interested in more details, you can consult the paper, which is published now in Theoretical Computer Science and also available in an archived version. So I come now to explain you the geometrical representations. So let me first fix the notation that maybe some of you don't know. The binomial coefficient of word Wx is the number of occurrences of X as a scattered subword of W, not factor, but just subword. For instance, to fix the notion, if you consider the word AA, BBA, and you want to count the number of AB, you can see on the right of the line there is four possibilities of AB as an subword occurrence of W. So there is the number of occurrences of X is 4. Of course, when the number we consider not when we consider later, the number of occurrences of the letter alpha is just the number that we usually denote as like this between pipe and alpha in subscript. Okay. So to provide you the representation of the binomial coefficient WAB, I start with the representation of the word W as usual. I represent an A as a horizontal segment and a B as a vertical segment. And here we have the representation of the word A, B, A, B, B, A, B, A, B, B, A. And now I want to count the number of occurrences of AB as a scattered subword. There is some formula, for instance, this one. To count this number, we can consider successively all prefixes of W that end with a B and count the number of occurrences of AB that end with this B. So we have just to count the number of A in the prefix P. So I start this computation here with the first B of the word. There is two occurrences of AB. Then I can consider the second B. We have four more occurrences of the word AB, and four more with the third B, and five more, and six more with the last B. And we can see that there is as many occurrences of AB as a scattered subword than there is square on the left of the left or the above the representation of the word in this rectangle. So this the interpretation of we can have of this binomial coefficient is that it is this area of this part of the rectangle which is just above the representation of the word. After that, we can, of course, see that with the quite same way, with that the part which is below the representation of the word is the number of occurrences of BA. This can be done with, for instance, this formula where we count the number of A in each suffix of the word that start with a B. Okay, this is the interpretation and comes quite naturally a formula that's maybe some of you already known, which is that the number of occurrences of AB in W plus the number of BA as occurrences of BA in W is exactly the product of the number of A and the number of B. This is quite clear in the picture since the height of the rectangle is the number of B's, width of the rectangle is the number of A, and we have already seen that the two parts are the sum of the two binomial coefficients. Okay, this is the geometrical interpretation of these two binomial coefficients I can provide to you. So I now want to use this geometrical interpretation to try to explain some known results about the two binomial equivalents. Let me recall that two words U and V are two binomial equivalent, and I will denote it with this equivalent to this notation, this relation. If the number of occurrences of X in U is equal to the number of occurrences of X in V, always in a third word, for all X of length 1 or 2. In the binary case, we can see that we do not need to look at all the words of length 2. We can just need to see the equivalence of two words for the two binomial equivalents. We just need to have the number of A to be equal, the number of B to be equal, and also the number of AB as occurrences of the two words. This follows first the formula that I have just explained and the well-known relation that counts the number of occurrences of the word alpha alpha in W, where alpha is a letter, which is the number of occurrences of alpha times the number of occurrences of alpha minus 1. This remark allows me to go to another binomial equivalent, which is a Paric equivalence. In 2000, Matejko, Saloma, and you introduced the notion of Paric matrix as over arbitrary alphabet, but what interests me here is only on the binary alphabet. And on the binary alphabet, the matrix is exactly this one. There is some zero below and someone on the diagonal, on the first diagonal, on the second diagonal. We have the number of A and the number of B, and we have finally the number of occurrences of the word AB as a word of U here. So, and we have exactly the three values that are used to see whether two words are two binomial equivalent. So it is immediate that two words U and V are two binomial equivalents if only if U and V have the same paric matrix. So this is one of the first result of the paper by Mathiescu, Saloma, and you in 2000. But this result was previously proved by Helmut Prodinger in his paper in 1979. And with this matrix was already appearing in this paper. Okay. One thing we can see with the geometrical interpretation is the fact we can have an explanation of the fact that the two binomial equivalence is a congruence, which means that given three forwards x, u, y, and v, the words x, u, y, and x, v, y are two binomial equivalent if only if the word u and v are binomial equivalent. This means that the number of letters in x, y, here it is a y, sorry, in x, u, y must be the same than in the number of A in x, v, y, which is quite immediate equivalent to the fact that the number of A in u is the same as in v. And we have the same thing for the number of b. And when we look at the number of occurrences of the word AB in U, we know from the previous geometrical interpretation that it is the area of the geometrical interpretation of the word itself. So we have this picture. We can split the area in 6 parts. And what is important is to say that to see that if we replace here the number of occurrences of U by the number of occurrences of AB in V, we have exactly the same areas here. So we can see that if U and V are two binomial equivalents, then also these two words XUY and XVY are two binomial equivalent, and conversely. The picture corresponds to this formula, which is above. Now I want to show that the the geometrical interpretation allow to explain also some result about a writing point of view of the two binomial equivalents. I'll introduce first the writing rules. So if you consider two words U, V, and V on the binary alphabet A and B, we write U right row V or V left row U. If U can be decomposed on the following way: a word X, the word AB, the word Y, the word BA, and the word Z, and V can be decomposed quite similarly, but replacing the first AB here with BA and the BA at the end here with AB. We can consider the reflexive closure and the reflexive and transitive closure of the relation left-right row. We denote this relation here, which means that we can rewrite one in one sense or in one direction or in the other direction. And we can also iterate the rewriting to go from one word to another word. In 2004, with Stéphane Fossé, we proved that for any binary word U and V, being two binomial equivalent is equivalent to be able to be rewriting from using these rewriting rules here. And I will explain how it works geometrically. First, what occurs when we switch AB to BA and BA to AB simultaneously? We can see with the the geometrical interpretation that the two area just above the representation of the word XAB, YB, and above the representation of the word X, BAY, ABZ are exactly the same. When we switch AB to BA, we decrease by one the area, but we also increase at the same time by one the area when we switch BA to AB. Of course, the number of A and the number of B in the two words are exactly the same, then we can see this way that if U can be rewriting to V with the previous rewriting rule, then U is two binomial equivalent to V, but this works in the other direction, and this also works if you reiterate the rewriting. So we can see that if we apply several times the rewriting rules, starting from word U and arriving to another word V, then the two words U and V are two binomial equivalent. For the other directions, assume that word U and V are two binomial equivalent. This means that the area just above the two representation, so here I represent the word U in the red line and the word V in the dashed line here. Of course, since the two areas are the same, and the words are not in this picture the same, then the gray part would show the difference between the two words. There is some gray part which must be above the red line and a part which must be below the red line, which shows that the two digitalizations of the words must cross in at least one point. Okay, so now we will consider the first part of the picture until, for instance, this crossing point. Then we can see that we need to have A followed by a B, since the red line starts with an A here. This is needed to meet the cross point. And when we continue and we are, the red line is above the dashed lines, then we must be somewhere have a B followed by a A. So I've marked here the 2 points to AB and BA. I see. And now, which quite naturally, we can try to reduce the kind of distance between the two words, switching this AB to BA and this BA to AB. So we obtain another word U prime, which is obtained by rewriting. And since from what we have just seen, we know that the two words are two binomial equivalent. And so the word U prime is also two binomial equivalent to the starting word, to the word V here. Now, the distance between the two words U prime and V is less, and you can see on the picture, and this can be theoretically proved. And so by induction of this distance, we can show that U prime the word V can be obtained by successive rewriting in one direction or in the other, depending on whether the successive word we consider start with A or with B. And so we can see that the word U also can be rewriting to V with the first rewriting rule just seen before. Okay. This and the proof of known result, and now I want to use this geometrical interpretation to show you other phenomena. First, there is some particular words in the two binomial class. If you rewrite successively a particular word, for instance, this word, in order to have no factor AB followed later by an occurrence of BA. For instance, if I replace this AB with this BA, we obtain this word. and then I iterate just to show what occurs. You can see that a B go on the left and the A go down. And if we reiterate several times, what occurs at one time when we have no more occurrences of AB followed by BA, we have this kind of pictures, which means that the word W belongs to the one of these two regular word language. That is a succession of B followed by a succession of A and a single B and some more A and finally some more B, or possibly no single B, just a succession run of B and followed by a run of A and a run of B. And we obtain so word that I denote final of W. And an important fact it is that the word we obtain by this successive rewriting does not depend on the initial word we consider in two binomial class. It just depends on the number of B, the number of A, and the number of AB, which is the surface, which is which is just above the representation. I will just give a more formal computation to see that. Okay. So I will write in order to have no occurrences of AB followed later by BA, but I can do the job in the other direction in order to have no factor on the form BA followed later by an occurrence of AB. And doing this, we are not going to split by something which is quite horizontal, but we are going to split the rectangle by something which is quite vertical. That is a word of this language. And we have a symmetric phenomena replacing the word A and the word B here. And once again, we obtain a word that I denote init of W that depends only on the two binomial class, that is the number of A, the number of B, and the number of occurrences of AB as a subword. Okay. This word to reinforce the fact that this word init and final doesn't depend of the initial word we consider but only of the binomial class, we can say formally that two words U and V are two binomial equivalents if only if they have exactly the same init representant and the same final representant. This is obvious when the number of occurrences of AB is 0. The word must be a run of B followed by a run of A. And so we have only one word in the two binomial class. When when we have more, at least one subword AB, which implies that the number of A must be non-zero and the number of B also must be non-zero. You can divide the number of occurrences of AB by the number of B, and with the quotient I and the rest J, we can construct directly the representation, the init representation, considering first I columns of A of initial A here and competing with JB here, and we obtain this word. So we can see with this formula that the word depends only on the parameters of the two binomial class. And we can do, of course, this job for the final representant with a quite similar formula, just inversing the roles of A and B. What I've just said can be rephrased on the following way. We can consider the graph G2 of W, whose vertices are the elements of the two binomial class, and the edges are the couple of words that are in relation with that can be rewrite from each other by the rule that I introduced before. And so this graph is connected. It is directed by the relation. It is acyclic because at each time there is something we make a rewriting, we can see that the word obtained by rewriting is lexicographic less, so we cannot find by successive application of the rule, we cannot find a word that we have already made. And it is expressed also between with this relation here. And there is a unique root of this graph, which is the init representant, and there is a unique sink, which is the final representant. So you have here an example of such a class here. What I presented before was not completely new. We can find these ideas in other forms in some papers. For instance, the direct computation of representants I provide you was already present in a paper by Tay and Kwa in 2015. The final representant appears in the proof of the next formula that compute the number of two binomial equivalent class of binary words for words of length n. And the init representant also appears in the proof, which is the proof that this particular language is regular. Well, no importance of what is the language, but it is just to mention that this init representant was already used before with other terminology and other way to use them. Okay. Another thing which was studied about the two binomial class was the number, the class of that are singletons. That was studied by Matthew and Salomon in 2004. And their results say that a word is unique in its two binomial equivalence if W does not have an occurrence of AB followed later by an occurrence of BA, and neither an occurrence of BA followed later by AB, or W belongs to one of these regular language, which shapes is represented here in these pictures. With what I presented before, we can add one item to this theorem quite naturally, since we know that the init representant of a word is equivalent to the finite representant of a word. If we want to have only one word, the two words must be equals, and this in quite immediately one is equivalent to 4. So it's time to show you the link with the partition of integers. This occurs when we try to enumerate words with a given number of occurrences of AB as well. Here we have the example for 2 occurrences of AB. If we consider 3 occurrences of AB, you have this picture, and maybe you can start seeing the partition of integers. We have is this partition in one part A3, here in 2 parts 2, 1, and 1 with the partition in 3 parts 1, 1, 1, which is here. When you will look at the words with 4 AB, we have these 5 shapes. Maybe there miss here a possible trailing run of B here. And maybe I can mention that if we fix the number of A and the number of B, maybe we cannot have all the representation, but if we have sufficiently many A and sufficiently many B's, then we can have the 5 pictures here, and so the 5 partition of the number 4 in here, and this make maybe once again clear when we consider the number of 5 as number of occurrences of AB in W. So this appears in the pictures, but we can do this more formally and with an ad hoc description of the word that we can can show that there is a bijection between elements of a two binomial equivalent class, and Ferrer diagrams, that is pictures of the partitions uh, into at most the number of A parts, and with larger parts at most the number of B parts. Okay, it's the number of B here. And what I presented in the picture before, it is the case where the number of AB in the world in the class is less than the number of A and number of B, and then the number of occurrences, the number of elements in the binomial class is exactly the number of partitions of the integer represented by the binomial coefficient here. Once again, this link between partition and binomial coefficient was already observed in 2015 by Tay and Kwa, under slightly different way, but it is the same links which was noticed by them. And to continue the talk, I must mention that we can observe that the graph that I have shown 2 slides before is not isomorphic to the correspondent lattice of partitions. Well, what is the lattice of partition? It is, so maybe I can specify what is a partition. The partition is just, as many of you know it, it is a sequence of decreasing integers, a sequence of decreasing sequence of integers, sorry, and whose sum is equal to n. And Brylawski in 1973 proved that the set of partition in n parts of an integer n is a lattice for a particular ordering, which is a dominant ordering, which is look like this. The partition lambda is greater than the partition mu if all the partial sums of the first coefficient in lambda I is greater than the number of coefficient, the integer in the partition of mu I. Yeah. And maybe what is interesting, it is that Brylawski 1973 shows that he proved when a partition covers another, meaning that there is no partition between the two partitions with the previous order here. This occurs when quite all the elements of the partition are the same, except in two integers, j and k, in which the integer lambda j is one more than the integer mu j, and the integer lambda k is one less than the integer mu k. And two cases can hold. One is that k is j plus 1, and the other is that the integer mu j is exactly the same mu k. This can be represented once again by some pictures. So I locally look at the partition. The first case corresponds to this one. We have the lambda, here the lambda partition, and here the mu partition, and there is a difference just at two neighboring position, and here, and this is the second case here. And what can be quite immediately see when we look partitions as words, it is that going from lambda partition to mu partition can be done by a locally rewriting, which is this rule, which quite the same rules than at the beginning of the talk, but here we do not have any word, we have just a power of b. And in the second case, we do not have a power of b, but a power of k. So we have a restriction of the rule, initial rule. I can say new writing, but it is just a restriction. And we can see in this restriction that the lattice, which is the graph of the binomial equivalence that we obtain using this restriction is a lattice, and it is isomorphic to the lattice of partition of the integer number of occurrences of AB with a technical restriction about the parts. Okay, we can exchange integer A and B, and inverse the number of parts and the multiple part bounded. YSPA, it is just just for special palindromes. And for who knows about rules, rewriting rules into two binomial for the two binomial equivalents, they can think to the palindromic amiable relation introduced by Atanasio and other co-authors in 2002, saying that two binary words are two binomial equivalent if and if they can be obtained by successively replacing one palindrome by another palindrome with same numbers of A and B. And what we have done just before, it is considering particular palindromes. Okay, so it's time to come to pair words. So, okay, sorry. So I've already defined pair word at the beginning of the talk. Just record it. We are studying words for which the number of currencies of AB and the number of currencies of B and W are exactly the same, whatever are the letters A and B. Maybe you can ask why is the name fair. You have here the introduction of Anton Chan in 2009. The idea was to find a way to schedule some order of passing a narrow door. Okay, and the approach of Helmut Poldinger in 1979 was, as I said, quite different. He considers the language of unrestricted Dick words as the words that have exactly the same number of A and the same number of B's. And he imagined to replace A and B by words X and Y, and called the language we obtained DXY. And he studied in his paper the language DABBA, which is exactly the language of a word we obtained quite exactly, since we do not have the number of A and the number of B that needed, but in his paper, he considered these restrictions. So binary pair words, if we want to represent them, we have here an example. What we need, it is that the part above is exactly the same as the part below the representation of the word. So in some ways, the representation of the word splits the rectangle diagonally in two parts of equivalent areas. Oh, exactly. So it means that this area, or the number of AB must be the product of number of A and the number of B divided by 2, which implies that, for instance, that there is no fair words that exist when the number of A and the number of B are both odd. Palindromes are examples of fair words. This is quite immediate when we consider in geometrical interpretation, the middle of the rectangle is a symmetrical point, the point of symmetry, and then by symmetry, one part is a map to the other part, and that they have the same area. But there is some fair words that are not palindromic, for instance, is one of the smallest lengths as possible. Here, it is not palindromic, but we can find in the two binomial class another word which is equivalent and which is a palindrome. For instance, this word BA, BA, BAB. So I mentioned that a fair word is nothing else than a word whose representation cuts in two parts of same area as a rectangle with the number of A and A the number of B. When we consider classical geometry, splitting the rectangle in two equivalent parts can be done using a segment. And we know that balanced words represent segments. I will not recall the definition of balanced words. I imagine that most of you know about it. So the natural question is, well, does there exist balanced fair words? And the answer is yes. For instance, for this example, we can see that the two binomial equivalent word is the following word. Moreover, not only there exists a balanced palindrome word for any binomial class, but we can also see that if we consider balanced words, being fair and being a palindrome is exactly the same. But the converse is not true. There exists in some two binomial class some it may have some different binomial representatives. For instance, here the two words ABBA and BAB are balanced and palindromal. I will now say something about the proof of these words. It use quite classical tools of balanced for balanced words. But one interest of this paper it is that it provides an answer to problem 23 in the paper of Anton Czerny 2009, proving that every fair word can be constructed from a palindrome using finitely many substitution or replacing of some proper factor, such as using a writing rule by a two binomial equivalent word. And we know this is true from what precedes, since for any word W, we know there exists a balanced palindromic word W. And moreover, we know that the being two binomial equivalent is the same that being that we can rewrite one word to the other. Okay, another way to answer the problem of Anton Czerny is to see that the two words that are the init representant and the final representant are both palindromes. The proof is quite immediate because being a final representant means that we are in one of these languages, the regular language, and if we add the hypothesis that the word is fair, we can prove quite immediate that in the two cases, the words are palindrome. Okay, and it proved, I explained it on the final representant, but this works exactly for the init representant. Okay, so the question of Anton Czerny was, what can we say about the number of binary fair words? The answers of Helmut Prodinger in 1979 was the following ones. First, given a word W, is associated to each letter a number m plus 1 or minus 1, depending of the letter is an A or an B. And he proves that the difference between the number of occurrences of AB in W and the number of occurrences of BA in W, it is this particular sum here. By a technical way, I don't know how to interpret this geometrically, but maybe you know here. And using this formula, when we are looking for fair words, we need that the left term is 0. So we have a sum on this way where there is some value epsilon, which is minus 1 plus 1, so that for given all the epsilon values, we have this sum which is equal to 0. And there is as many fair words and as many ways to have this sum equals to 0. Then using various technique, it proves that it provides an asymptotic estimation of the number of fair words, which is this one here. Okay. Another way to look at the number of binary fair words can be to ask whether there is, it was already known, and looking at the online encyclopedia of integer sequences was quite immediate from the paper of Cherry in 2009 because he provides the first 21st value, the 31 first value. And well, the sequence of errors was not known in the encyclopedia, but another sequence appears for the same first values, which is the sequence of this kind of object that I will describe later. And so the natural question is, well, are these object and ferrules are exactly the same, or are they equivalent? So I have to explain these objects that are related to the least square approximation method, which is an approximation method which consists to minimize this sum, where here xi, yi are some points, and f is a parameterized function that act as a model, and we want to have the parameters such that the sum is minimal. Okay. In our context, we have a word W, so W1, Wn, where on the alphabet 0 and 1, and the points are the index of the letter and the value of letter for each letter of the word. And we want to have to approximate the points by the straight line, which this equation. So we consider the function x that maps x to alpha plus beta x, and the question, this object here are the object we obtain when we minimize the sum when beta is equal to 0. Okay, and we can prove indeed that the sum is minimal when beta equals 0, exactly when the word that is used is fair. Moreover, we can have the exact value of alpha. Let me provide you some quick explanation of the proof. So I set G the maps that maps each alpha beta on this sum, and then to minimize its value of G, we compute the partial derivation. And what is interesting it is that the derivation with respect to alpha implies that the use of the number of 1 in the word W. And when we derive with respect to beta, we have the sum of position of 1 that appears. And the next step of the proof is to consider that beta equals 0, and then for minimizing, we have the two relation before shows that we must have the two following equations, and then it was quite just computation to have the equivalence here. But we also need a result obtained with Stéphane Fossé in 2004 that shows that the sum of positions of 1 is related to the number of occurrences of 0, 1 in the word W plus this particular value here. So here are the main ideas, and just after it is completely direct computation here. Okay, and this is just for one way, but the second way, the converse way of the proof, acts exactly similar. Just to say that we can, with the same result of Fossé and Richomme in 2004, we can show that the word W is fair if only if they have the same sum of position of bees. And this is interesting because this answers a conjecture that occurs in the online encyclopedia of integer sequence. Yeah. Okay. Don't escape the proof. And maybe something that explains the proof, it is that there is also a geometrical interpretation of the sum. We have just to change the representation of the word, and we make appear the sum of position of a B and another sum that I do not detail here. Okay, so time going on, so I think that I'm going to skip the next question and going to conclude, sorry, now. Um, so some questions to you. First, well, I'm will be interesting to have a geometrical interpretation of the following Schrödinger formula between the difference of the number of A, B, and BA. And let's see how to interpret that. Natural question to conclude is also that is there any other binomial coefficients that can be geometrically interpreted? The situation seems to be very particular, and so I'm not very optimistic about that. And the next question is the original Chinese question where can we count more precisely the number of fair words over an arbitrary alphabet? We have some answers on binary alphabets, but what occurs for arbitrary alphabet? Can the fact that a word is completely and uniquely defined by this projection on binary alphabets, and at the same time, a word is fair if only if its projection by alphabets are fair can be useful? Well, I don't know, and I will stop here for this talk. Thank you for your attention.
Great. Thank you very much, Gwenaël. Does anyone have any questions? Hajime.
So thank you for a nice talk. And I'm not as good at this part, but so I have an interest in rich words. Is it possible to count the number of rich and fair words of length k? Is it
The number
of fair words which is rich?
I don't know. I have not. I do not investigate this question.
So you've considered in some sense terminal favors. So I'm also interested in rich favors.
Okay.
Anyway, thank you.
Christophe.
Thank you, Gwenaël, for this talk. I wonder if there exists Linden words which are fair on a binary alphabet, I mean, or it's not possible to have fair Linden words.
I do not completely investigate this question, but when looking at balanced words, my first attempt was to look at the Christopher words, and I'm quite sure that there do not exist Christopher words, but I do not investigate general Linden words.
Mm-hmm. Yes. Mm-hmm. Thank you.
Yeah, Jeff, did you have a question?
Yeah, maybe I missed it, but would there be any interesting generalization, for example, to words for which the binomial coefficient of every permutation of ABC is the same? Let's say where A, B, and C are distinct letters.
Oui, c'est ça.
Open question for me. I don't know. I there is some attempt to look some things like that when in the generalization of a Parric matrix, where they try to have some equivalence between fixing some numbers, but maybe not exactly this question. Okay, I don't know.
Thank you. Nice talk.
Thanks.
Are there any other questions?